Welcome back to my class in statistics. Today we will derive a formula for calculating standard deviation. This formula will give a better measure of dispersion for a set of data and a standardized coefficient of variation. Thus, this formula is derived from the original formula for variance, denoted by S squared for sample variance. The formula for sample variance is as follows. The sample variance denoted by S to the power 2 is given by the summation of the square of the difference between each x value and the mean of the sample of values divided by n minus 1. And this expression, the square of quantity x minus x bar is said to be the square of the deviation of the value x from the mean. And the deviation of x from the mean can be 0. That means the value x is exactly equal to the mean. Or the deviation of x from the mean is negative, which means that the mean is greater than the x value. Or the deviation of x from the mean is positive, which means that this particular value of x is greater than the mean. Thus, to eliminate the signs, the negative, the positive signs, we take the square of the deviations of the x values from the mean. And we get the summation, and the summation is divided by n minus 1. And that value is defined as variance or variance of the sample denoted by S squared. And the formula for standard deviation is derived from this formula for sample variance by simplifying the expression at the right hand side of this equation. And we start with the square of quantity x minus x bar. To get the square of x minus x bar, we apply one of the special product rules in college algebra. From algebra, we have the square of a sum or difference of two quantities denoted by a and b. If we have the square of a plus b, the first term is a to the power 2. The second term is twice the product of the two terms a and b with a positive sign. And the last term is the square of the second term b. If you have the square of a difference a minus b squared, the first term is the square of the first term a squared. The second term is twice the product of the two terms. And if you want the square of the difference a minus b, the second term is negative. And the last term is positive. The square of the second term is negative b, and the square of negative b is positive b squared. Hence, the last term is plus b squared. To write the expansion of the square of x minus x bar, we apply the special product rule for the square of the difference of two terms, or the square of a minus b, where our a in this expression is x. Again, in particular, we apply the special product rule, the square of difference. a minus b, which is equal to the square of the first term a minus twice the product of the two terms a and b plus the square of the second term b, where a in this expression is x, and x is a variable. It can be any of the values in the given set of data, and b is the mean x bar, and x bar is a constant because it is a numerical value, a single numerical value, defined as the summation of x divided by n. If you divide the summation of x divided by n, you get the single numerical value denoted by x bar, and is defined as the sample mean. So we write the expansion of the square of x minus x bar by replacing a with x and replacing b with x bar. Hence, by the square of the difference of x minus x bar, we get the square of the first term x, x squared, minus twice the product of the two terms, x multiplied by x bar, plus the square of the second term, x bar, x squared. The last term is the square of the second term x bar, denoted by x bar square. Now we apply one of the properties of the sigma notation, or the sign for summation. One of the properties of summation says that the summation of the sum or difference is equal to the sum or difference of the summations. Hence, summation of x plus y is equal to summation of x plus summation of y. If you have the summation of x minus y, then summation of x minus y is equal to summation of x minus summation of y. And it's like we distribute the sigma notation to each of these terms of this trinomial. In algebra, this is a trinomial, an algebraic expression with three terms. And we simply distribute the sigma notation. Hence, by this property of sigma notation, the summation of quantity x squared minus 2x x bar plus the square of x bar is equal to summation of x squared minus summation of 2x x bar plus summation of x bar squared. Now we divide each term by the denominator n minus 1. And to x bar, we use the formula for x bar, or sample mean. X bar is equal to summation of x divided by n. Dividing each term in the numerator by n minus 1, we get summation of x squared divided by n minus 1 minus summation of 2 times x bar divided by n minus 1 plus summation of x bar squared divided by n minus 1. To the second term, 2 here is a constant and x bar is a constant. And we apply again another property of sigma notation to simplify the second term. Another property of summation says that the summation of the product k times x, x is a variable and k is a constant, is equal to the constant multiplied by summation of x. It is x that varies. It is the value of x that varies. If you are getting the summation of n values of x, then the index of the summation will go from 1 to n. But k here is a constant, so if you have summation of a constant times a variable, you can take the constant out of the summation. Summation of constant times x is equal to the constant times summation of x. And in the second term, the constants are 2 and x bar. So we can take this out of the summation. By applying this property of the sigma notation or summation, the summation of 2x multiplied by x bar over n minus 1. N minus 1 is actually a constant. So 2x bar divided by n minus 1 is a constant. And we have taken 2 multiplied by x bar, a constant. 2 is a constant, x bar is a constant. So 2 times x bar is a constant. We take those out of the summation. The second term now is equal to minus 2x bar multiplied by summation of x or all over n minus 1. And the last term is the same. Now we can simplify the numerator using another property of summation. The other property of summation says that the summation of a constant from I is 1 to n. That means you are adding the constant x bar n times. That means summation of x bar for I is 1 to n is equal to x bar plus x bar plus x bar. The summation of a constant x bar for I is 1 to n means that you are adding x bar to itself n times. And instead of writing this long addition, we simply write the summation of x bar, constant x bar for I is 1 to n is equal to n multiplied by the constant x bar. And in the last term, applying this property of summation, the constant is x bar squared. X bar is a constant, raised to the power 2 x bar square is still a constant. And summation of x bar square means that we have to add x bar square to itself n times. And we add x bar square to itself n times because our sample size here in this formula is n. And applying this property of sigma notation, this last term now is equal to n multiplied by x bar square divided by n minus 1. Hence, the last term by this property of sigma notation is equal to n. And because we, in this notation, summation of x bar square, we are adding x bar square to itself n times. Hence, this summation of x bar square is equal to n multiplied by the constant x bar square divided by n minus 1. Now, in the second term, x bar, and in the last term, x bar, we replace it with its value for x bar, summation of x divided by n. We replace x bar here with summation of x over n. We replace x bar here with summation of x over n, and we square it. And then we simplify this trinomial. We now continue by replacing x bar in the second term and x bar in the last term with summation of x divided by n. And we will simplify this trinomial. We have x squared equals, the first term is the same, summation of x squared divided by n minus 1. The second term is minus 2 multiplied by x bar. We replace it with summation of x divided by n. Multiply by summation of x over or divided by n minus 1. And the last term is, we have n divided by n minus 1. Multiplied by the square of x bar, where x bar is summation of x divided by n. We replace x bar with summation of x divided by n, and we square it. The first term is the same. Now we multiply the numerators and we multiply the denominators. The second term is minus 2 times summation of x multiplied by summation of x is equal to 2 times the square of summation of x. Because we multiply summation of x by itself, hence summation of x times summation of x equals summation of x squared. Divide by, we multiply the denominators and multiply by n minus 1. In the last term, we apply one of the properties of exponents. Again, from algebra, one of the properties of exponent says that the square of a over b is equal to the square, the a to the power n divided by b raised to n. The square, the a over b to the power n by this property of exponent is equal to a to the power n divided by b to the power n. And we apply this particular property of exponent to this square of summation of x over n. So we take the square of summation of x divided by the square of n and multiply by n divided by n minus 1. And you can see that we have n in the numerator and n squared in the denominator. And we can simplify n over n squared if we cancel n in the numerator, or divide n in the numerator and divide n squared in the denominator. N divided by n is 1. And n squared divided by n is n. First term is the same, the second term is the same, and the last term now is square of summation of x divided by n multiplied by n minus 1. The last term is summation of x is square, or square of summation of x divided by n multiplied by n minus 1. We write first n multiplied by n minus 1, so that the denominator of the last term is the same as the denominator of the second term. Now we take the LCD of the denominators, the lowest common denominator. Just multiply all the factors that you see in the denominator, and if the factor appears with different exponents, you take the highest exponent of that factor. N appears twice in the second and in the last term, the denominators of the second and the last terms, and the highest exponent of n is 1. And we multiply n by another factor that you see in the denominator, and that factor is n minus 1. And the highest exponent of n minus 1 is 1. The exponent of n minus 1 in the denominator of the first term is 1. Here it's 1, here is 1. If the exponent of n minus 1 in the denominator of the last term is 2, then you multiply n by n minus 1 squared, or to the power 2. But the highest exponent of n minus 1 is 1. So we multiply n by n minus 1 raised to 1, or simply n multiplied by n minus 1. Now we find the numerator by dividing the LCD by each denominator and multiplying the result by the numerator. And multiplied by n minus 1 divided by n minus 1 is n. Multiplied by the numerator, you get n times summation of x squared. Minus LCD n multiplied by n minus 1 divided by n multiplied by n minus 1 is 1. Multiplied by the numerator, you get 2 times the square of summation of x. And finally, the last term, LCD, n times n minus 1 divided by n times n minus 1 is 1. Multiplied by the numerator, square of summation of x, you get square of summation of x. Now we combine like terms in the numerator. The second and the last terms are like terms or similar terms because they have a common coefficient of square of summation of x. In the second term, the coefficient of square of summation of x is minus 2. In the last term, the last term should be square of summation of x. In the last term, the coefficient of the square of summation of x is 1. And the common coefficient is the square of summation of x. So we add the numerical coefficients, minus 2 plus 1 here is minus 1, multiplied by summation of x squared. This is now the formula for sample variance that will give you a value of standard deviation that is more accurate and that will give you a standardized coefficient of variation. In the last lesson, we used this formula to compute for the standard deviation of a sample, and in the denominator we have n minus 1. In the formula now for variance from which we can obtain the standard deviation, the denominator n minus 1 is multiplied by n. Hence, this factor n in the divisor or denominator will make this quotient smaller. And this is the correction factor that I was telling you earlier to calculate for the value of standard deviation that will give a standardized coefficient of variation. We now take an example. For our example, for using the formula for variance from which we get the standard deviation that will give a more accurate value of standard deviation with corrector factor n in the denominator, consider the following set of sample data: 9, 10, 3, 7, 5, 2, 8. These values are denoted by the variable x. And n is the sample size, n is the number of values given in the set of data. We simply count the number of numerical values given: 1, 2, 3, 4, 5, 6, 7. And the sample size is 7. In this formula for sample variance, we need the summation of x squared. And before we can get the summation of x squared, we need to get the square of each x value. Hence, we get the square, we take the square of each of these numerical values in the given set of data. 9 square is 81, 10 square is 100, 3 square is 9, 7 square is 49, 5 square is 25, 2 square is 4, and 8 square is 64. Now we can get the summation of x squared by simply adding the square of x values. 81 plus 100 plus 9 plus 49 plus 25 plus 4 plus 64, and you should get 332. And that's the summation of x squared. In the formula for sample variance, we also need the square of summation of x. And before we can get the square of summation of x, we need to get the summation of x values by adding the values of x. 9 plus 10 plus 3 plus 7 plus 5 plus 2 plus 8 equals 44. And that is the value of summation of x. We now substitute the value of n, summation of x squared, and summation of x into this formula. And s squared is equal to n is 7 multiplied by summation of x squared 332. 7 multiplied by 332 minus the square of summation of x. Summation of x is 44. Hence we have minus the square of summation of x, 44. All over n is 7 multiplied by quantity 7, n is 7 minus 1. 7 minus 1. And using your calculator, multiply 7 by 332, you should get 2,324 minus the square of 44. If your calculator is not scientific, 44 square is the same as 44 multiplied by 44. And you should get 1,936. Divide by 7. 7 minus 1 is 6. Now we get the difference of 2,324 and 1,936 using calculator. You should get 388. In the denominator, we have 7 multiplied by 6. So we divide 388 by 42. 388 divided by 42 using your calculator, you should get 9.24 rounded up to 2 decimal places. So the variance, sample variance denoted by s squared is 9.24. And the standard deviation is defined as the principal root of the variance. That is the square root of the variance s squared. And from the earlier lesson, we defined principal root as the positive root of the positive real number. Because we said that any positive real number has two roots, one positive root and one negative root. But the standard deviation is the principal root or the positive root of the variance. And the variance s squared is 9.24, so we take the positive root or principal root of 9.24, and using your calculator, you should get 3.04. This is the sample is standard deviation. Now we can calculate the coefficient of variation. And we said earlier, in the earlier lesson, that coefficient of variation expresses the standard deviation as percentage of the mean. That is why the mean x bar is in the denominator. Because we want to express the standard deviation as percentage of the mean. And multiply by 100% to convert this quotient to percentage. And to calculate the coefficient of variation, we need the standard deviation, which we already have 3.04, and the sample mean. And the sample mean x bar is given by summation of x divided by n. Our summation of x is 44, and our sample size n is 7. 44 divided by 7 to 2 decimal places is 6.29. Hence, the coefficient of variation is standard deviation 3.04 divided by the mean x bar 6.29. You divide 3.04 by 6.29, and the result in your calculator multiply by 100 and rounded up to 2 decimal places, you should get 48.33 and add the percent sign. I said earlier that this is the formula of variance from which you can get a standard deviation that will give you a standardized coefficient of variation. It is because using this formula for calculating the standard deviation with corrector factor n in the denominator will give you a coefficient of variation that will never exceed 100%. And that is what is meant by standardized. That is what is meant by when we say the coefficient of variation standardizes the standard deviation. And this completes our example for using the formula for computing standard deviation with corrector factor and in the denominator. For your practice, please try the following exercise. Find S squared sample variance or sample variance. Find S standard deviation or sample standard deviation and coefficient of variation. In all these three, you will use the formula that we have derived today, the formula for computing the sample variance and standard deviation with corrector factor n in the denominator. And the given here is a sample data for diameters of bearings, and the unit is centimeter. So this 1.21 centimeters, 1.25 centimeters, 1.03 centimeters, 1.11 centimeters, and 1.19 centimeters. And you will find the sample variance, standard deviation, and coefficient of variation. And one way to check if you are correct is that the coefficient of variation should not exceed 100% using the formula that we have derived today for sample variance and sample standard deviation. And that completes our lesson for today. Thank you for joining me in my class today in statistics.